I put this slide up not because I want to sell you any books, but because several students asked me about references, and these are some very good books on the foundations of quantum mechanics that I can definitely recommend. And there are also, of course, a series of very good papers that I cannot mention all. So in particular, the speakable and unspeakable in quantum mechanics is like the Bible if you want to get started on foundations. This is the collected papers of John Bell. Basically, we owe it to John Bell that people started thinking about foundations of quantum mechanics again and started questioning the Copenhagen dogmas. So there are some very brilliant articles in there. But these are all very good books. So there's a textbook on Bohemian mechanics. There are this quantum physics without quantum philosophy. I like the collected works of Detlef Dürr, Shelley Goldstein, and Nino Zanghi, which develop Bohemian mechanics in the modern form today. Making Sense of Quantum Mechanics is also a very good book by Jean Bricmont, which is special because it also discusses a bit the political and philosophical backgrounds and so on. And Sneaking a Look at God's Cards is by Giancarlo Girardi, who is like the G in the GRW theory, so the one who came up with the first collapse model, so to speak. But again, I don't want to sell you any books. This is just in case you are interested in some references. Let's get started with today's topic, which is quantum equilibrium. So the questions, how do we get probabilities in quantum mechanics, in particular in Bohmian quantum mechanics under the Pauli-Bohm theory, and how do we get operators as observables? How do they arise in quantum mechanics? Because usually they are said to play a very central and fundamental role. They are supposed to be that which connects the quantum formalism to observation. If you have a precise formulation of quantum theory, you see that they arise very naturally from an analysis of the theory without having to postulate them as fundamental. And in fact, I think they are not. But the question of probabilities is, of course, a very central one and a very subtle one. And we discussed yesterday in some detail Bohmian mechanics, which is a deterministic theory, and I try to present you some prima facie virtues of this theory, but of course everything is meaningless if we cannot account for the experimental data, which in quantum mechanics is mostly statistical predictions that are confirmed with very high accuracy. So one question that you might ask is, how do we get probabilities at all if the theory is deterministic? But in fact, you shouldn't be all too worried about that, because we know how this works already from classical mechanics and classical statistical mechanics, mostly due to the work of Ludwig Boltzmann. So a lot of what we will discuss here will follow the footsteps of Ludwig Boltzmann and his statistical mechanics. So to summarize from yesterday's lecture, we have Bohmian mechanics, which is defined by two equations. We have the Schrödinger equation for the evolution of the wave function, and we have the Bohmian guiding equation for the evolution of the configuration, so the particle positions. And on the fundamental level, if we take the theory seriously, we have to talk about the wave function of the universe. So the only really closed system, so to speak, is the universe as a whole. So on the fundamental level, we have to talk about the universal wave function here, that in principle, although of course we will never be able to compute it, but in principle, it guides the time evolution of all the particles in the universe. But of course, in practice, we do not want to always to work with the universal wave function, which we don't even know what it is, but we want to be able to give an effective description of subsystems in a laboratory in particular. And we discussed yesterday how this goes. We split the configuration space into configurations of the subsystem and configuration of the environment. And we define a conditional wave function of the subsystem by taking the universal wave function and plugging in the actual configuration y of t of the environment of the rest of the universe, and we get a wave function that depends on degrees of freedom of the subsystem only. And in some situation, when the subsystem decouples suitably from the environment, this conditional wave function becomes an effective wave function. So we can have a description of a nice Bohemian subsystem, which has again this Bohemian form. So again, an independent Schrödinger evolution for the effective wave function and a guiding equation for the subsystem, which depends only on this effective wave function. And this is what corresponds to the usual quantum mechanical treatment of a subsystem. In particular, the statistical analysis, the statistical description always refers to subsystems, into ensembles of subsystems. So when we want to recover the statistical prediction of quantum mechanics, we have to recover them for ensembles of subsystems prepared with a certain wave function. So the first important step is the so-called quantum equilibrium hypothesis. So as you've seen and as we've said, in Bohemian mechanics, a subsystem or any system at all has an actual configuration. So it consists of particles that have an actual position in space and move according to a well-defined law of motion. Now we make a statistical hypothesis, which is that in an ensemble of independent subsystems with conditional wave function psi, the particle configuration Q is distributed according to the quantum equilibrium measure, which is of course just Born's rule. So if you have an ensemble of subsystems with wave each independent of each other with wave function psi, then the configuration of the system is distributed according to psi square, where psi lives on configuration space of the system. So this is just the familiar Born rule. Okay, now this is important, but it's just a hypothesis, so nothing was proven yet. But the first important property that we have to note is equivariance. Equivariance means that we have a conservation of probability under the Bohemian flow. And if you remember yesterday how I motivated the Bohemian guiding equation from the continuity equation, this shouldn't surprise you, because the Bohemian guiding field together with this psi square distribution satisfies a continuity equation, which just gives you the conservation of probability. But there is a natural way to evolve a measure with time. So if you have a measure here at time 0, this is a measure of some measurable set, and then you evolve this measure with the dynamics, then so naturally it involves like this. So the measure of a set at time t is just the initial measure at time 0 of the set that under the time evolution has evolved into the set A. Okay, so you have here the set A, and under the time evolution, the set has evolved from, so this T is here, the flow. Right, so at time T, the measure of the set at time T is the measure of this origin set at time 0. This is just how any measure naturally evolves under a flow. But the interesting property here is that we have this equivariance property. So if this measure is defined through the density psi 0 squared, then this measure, and this is not trivial, so this is just a definition, but this is not a definition, this is a result that you have to check, that you have this equivariance property. So this is the natural generalization of a stationary measure. So a stationary measure would be, for instance, in classical Hamiltonian mechanics, the Lebesgue measure on phase space is a stationary measure. It doesn't change under the dynamics. But here we have a non-autonomous system. We have a time-dependent velocity field in general, so we cannot expect a stationary measure. But the next best thing is an equivariant measure. And again, the equivariance property is that if the measure at time t0 is given by psi 0, the measure at time t is given by psi t, where psi t is just the solution of the Schrödinger equation with this initial wave function, psi 0. So this is the conservation of probability. And this means that if the quantum equilibrium hypothesis holds at one time, then it holds at every time t. Okay, so if we have an ensemble of Bohemian subsystems that are distributed according to psi square at time t0, then they are distributed according to psi square at all later in earlier times. Okay, this is not, again, not enough, but this is already something, right? If we go back to the example of the double slit experiment, and you have here an ensemble of particles, so one after one, they are sent in from here, okay? And those are the trajectories, again, for different initial configurations, so additional, different initial data. So if you have these particles, this ensemble of particles then comes in, and if it's distributed according to psi square here, where it comes in and hits the slit, then it will be distributed according to psi square there, where it hits the screen and you see the interference pattern. So if you have a psi square distribution here, you will get exactly the quantum mechanical probabilities there. Yes? So first off, there's no collapse here in the sense of orthodox quantum mechanics. There's just the effective collapse in the sense that we discussed yesterday. There's in particular no measurement problem here, because you always have a definite trajectory and you always have a definite outcome. But as far as the statistical analysis goes, we are not done yet. As I said, this is not everything, but this is already something, right? We know that if you have the psi square distribution here as the particles come in, you have the psi square distribution there as the particles hit the screen, and you have the interference pattern, exactly the probabilities predicted by quantum mechanics. But of course, this is, to some degree, shifting the problem to why should you have the psi square distribution here, right? So as I said, this is already something, the conservation of probability. If this quantum equilibrium hypothesis holds at one time, it holds at every time. But now the question remains, why should this quantum equilibrium hypothesis hold at one time to begin with? Was there another question? Yeah. Okay, right, that is the right question. So you're on the right track. This is the right question to ask. So again, this conservation of probability is important. If the quantum equilibrium hypothesis holds at one time, this quantum equilibrium hypothesis holds at all times, but now we have to understand why should it hold at any time? Why should there be a time where the quantum equilibrium hypothesis holds? So the question is, in other words, how can we justify this quantum equilibrium hypothesis? And as I already announced, we should go back to classical statistical mechanics, to what Boltzmann told us about the justification of the statistical hypotheses of classical mechanics and classical statistical mechanics, and it will turn out that we can use the very same strategy. So here's an important result from classical statistical mechanics. If you have an ideal gas in a box, then you will find the Maxwell-Boltzmann distribution of velocities for its particles. Okay, the Maxwell-Boltzmann distribution is essentially a Gauss distribution depending on the temperature of the system, so depending on the kinetic energy that is in the system. So here you see the plots for different values of the temperature. Those are all Maxwell-Boltzmann distributions, and this is, so to speak, a probability law, a statistical law for the distribution of velocities in an ideal gas. Okay? And now, also keep in mind the underlying theory here is just classical mechanics, so Newtonian mechanics or Hamiltonian mechanics, if you prefer, which is a perfectly deterministic theory. Okay, so there's nothing intrinsically or fundamentally random about the distribution of velocities in a gas. But nevertheless, we have here a very strong statistical regularity, which is that if we look at an ensemble of particles in this box of gas and we measure their velocities, we will find a very good approximation, such a Maxwell-Boltzmann distribution. So here too, we have a statistical regularity that arises from a deterministic theory. And the question is now, how can we justify or derive this Maxwell-Boltzmann distribution from the deterministic theory, which is Hamiltonian mechanics? And Boltzmann's argument, essentially, just in words, before we give it some more flesh mathematically, what he says in his lectures on gas theory is the following. The ensuing most likely state, which we call that of the Maxwellian velocity distribution, it was Maxwell who first found the mathematical expression in a special case, is not an outstanding singular state, opposite to which there are infinitely many more non-Maxwellian velocity distributions, but it is, to the contrary, distinguished by the fact that by far the largest number of possible states have the characteristic properties of the Maxwellian distribution, and that compared to this number, the amount of possible velocity distributions that deviate significantly from Maxwell's is vanishingly small. Now he goes on to explain, I don't know why I didn't cite it, that what it means to say by far the largest number of possible states is given by the stationary Liouville measure, which is just the Lebesgue measure, the usual volume measure on phase space, which is just the fundamental state space of Hamiltonian mechanics. So now here, there's a lot in there in this statement that we will try to disentangle a bit. So we have one box of gas, just this very box of gas, and this box of gas has a microstate. That is what it is. Even if you don't know it, it has a definite microstate. That means every particle, every single particle, and we have about 10 to the 23 particles in a box of gas, has a definite position and a definite momentum, a velocity at any time. So this microstate is what it is, and it determines exactly the velocity of each and every particle. Nonetheless, there's a very strong statistical regularity, which is that if we look at a large enough number of particles and look where their velocities are, we will observe, to a very good approximation, a Maxwell-Boltzmann distribution. And now how does Boltzmann explain this statistical regularity? He explains it by the fact that the Maxwell-Boltzmann distribution is the distribution of velocities that you will find in by far the largest number of possible states that the box of gas could be in. So more schematically, we have here, think of that as the phase space of the box of gas, a very high dimensional phase space. And we are in momentum space, we are on a sphere because we have a conservation of energy, we have a constant energy. So this means that just that the sum over p squared is a constant, twice times the mass of the particles, so they are all having the same mass, twice the energy. And the actual microstate of a system is just 1 point in this phase space. And one point in this phase space determines the actual state of this box of gas. And it also determines the velocity of every single particle. But if you look at an ensemble of very many particles, okay, and look at the distribution of their velocities, now here I've plotted just 9 of them, but of course, to see a good statistical distribution, you will have to look at a much larger number. But if we look at many, many particles in this box of gas and look where exactly their velocities are, we will find a distribution that is approximately given by this law here, by the statistical law, which is the Maxwell-Boltzmann distribution. And now Boltzmann explains to us that this is the kind of distribution, okay, that we would find here not for one very special state, but for almost all possible states that the system could be in. Okay? And this is, of course, what we call the thermodynamic equilibrium. So the Maxwell-Boltzmann distribution is the equilibrium distribution. It is the distribution of velocities in an ideal gas that we would find for almost all possible microstates that the gas could be in. And this is a computation that one could actually do, so it's not that difficult, but you just have to look at the measure, basically, of all the microstates on this energy shell, such that the velocity of a particular particle lies between an interval A and B. So this is basically just a conditional probability starting from this microcanonical measure. The microcanonical measure is just a Lebesgue measure, the natural volume measure on phase space, restricted to this constant energy shell. And you will see that for large n, you do the limit such that you keep fixed the average kinetic energy per degree of freedom, you hold that fixed. And you see that for large n, this conditional probability is approximately given by this density here, which is just Maxwell-Boltzmann density. This is, if you've never done this computation, it's really not very instructive to do it at least once. And from this conditional probability formula, we have a law of large numbers result. So this here, let me explain, is an empirical density. This psi here, or chi, is the characteristic function. So this is 1 if the velocity of particle I set here in x direction, lies within this interval, and 0 if it doesn't lie within this interval. So for the microstate x, x is the microstate of the system that again determines position and velocity of every single particle. So this is just the number or the density or frequency of particles in this box of gas whose velocity lie within the interval A and B. Okay? And this is close to this expression here, given by the Maxwell-Boltzmann distribution for the largest, by far the largest number of microstates. So this means that the measure of possible microstates for which this empirical distribution differs from the Maxwell-Boltzmann distribution by more than this small epsilon goes to 0 as n goes to infinity. So this is exactly just in precise mathematics what Boltzmann said in this quote. Okay, the possible microstates of the system for which the actual distribution of velocities that we find in the gas is given to very good approximation by this Maxwell-Boltzmann distribution. Okay, the measure of these microstates goes to 1. So they are almost all as n goes to infinity. So if we have a sufficiently large number of particles, almost all microstates are such that they show the Maxwell-Boltzmann distribution of velocities. So again, this is a relatively subtle argument. And the argument is that the stationary microcanonical measure here is not a probability measure. So our box of gas just is what it is. It is just there, and it has one microstate, one definite microstate that evolves according to deterministic dynamics. Okay? But we find this regularity in this box, namely the velocity distribution according to the Maxwell-Boltzmann law. We want to explain this regularity. And this microcanonical measure is a typicality measure that tells us what are typical microstates, typical initial conditions for this box of gas. So it allows us to make a statement about regularities that we find for almost all possible microstates, or almost all possible initial conditions. So the role of this typicality measure is to define what we mean, or what Boltzmann means when he says by far the largest number of possible states have the characteristic properties of the Maxwellian distribution. That is, in other words, the role of this typicality measure is to define equilibrium. And again, this measure is distinguished by the fact that it is stationary under the Hamiltonian dynamics. And now in Bohemian mechanics, we do a very analogous reasoning, okay? So the universe, think about this box of gas as a model for the universe. It is a closed system that exists once and only once, and it evolves according to deterministic dynamics. And it is what it is, just as our universe is what it is. Okay? We do not have an ensemble of universes in which we look for statistical regularities, but we have only one universe in which we look for statistical regularities. So think about this as the configuration space of the universe, which according to Bohemian mechanics is the fundamental state space. And our actual universe corresponds to just one state in this configuration space, one point in this configuration space. And this one point determines all the statistical regularities that we find for subsystems. But if we have an ensemble of independent subsystems, so approximately of this form, plus here something that belongs to the environment, so this would just be the ensemble of independent subsystems, all with effective or conditional wave function phi here, and you look at the distribution of particles in this ensemble of subsystems, you will find approximately, to very good approximation, a distribution that is given by little phi square. Okay, so you will find a distribution that is given by Born's rule, which is here the analogon to the Maxwell-Boltzmann law in classical statistical mechanics. And yes, it comes now. So this is what we basically, so this is first what we find empirically. We have an ensemble of distribution, ensemble of subsystems with wave function phi. So the configuration of each of them is determined precisely by the configuration of the universe as a whole. But if you look at the statistical distribution, we find a very good approximation, a phi square distribution. And now we want to derive or explain this regularity, and we do this as follows. So we look at the conditional probability. This is the measure defined by the universal wave function. So we look at the measure of all configurations of the universe, x and y, conditioned on the actual configuration of the environment, y. So that we hold fixed, we condition on the actual configuration of the environment, and now we ask what is the measure of the set for which x lies in some infinitesimal interval, dx. And now we find exactly that expression just by plugging in y into the universal wave function, into the universal psi square measure, which is nothing else than the psi square measure of given by the conditional wave function. Yes, I will say something about that. So it's then important to distinguish this measure from that measure. They have a different status. They are not equal. I will come back to that. First, what I want to point out is that this conditional probability formula is very easy to see, that it holds. That is not extremely helpful because here we have conditioned on the configuration of the entire rest of the universe. Basically every single particle in the universe that does not belong to our subsystem of interest. And of course we have no chance to knowing what this y is. So this formula is correct and important, but it's not extremely helpful. However, now we can do a little trick, which is that it doesn't matter, so we can condition on all the y's, on all possible y's, that give us the same conditional wave function for the subsystem. Okay? And then the condition, then it's just a simple property of conditional probabilities that we get here the same conditional probability no matter on which y we condition. So now we do not condition on any particular configuration of the universe. We condition on the set of all configurations of the rest of the universe such that our conditional wave function for the subsystem is psi. And this is something that in general we can know. That is in particular when we prepare the wave function psi for the subsystem. Okay, when we prepare the wave function psi for the subsystem in the laboratory, then we know that the wave function of the subsystem is psi, and we know that the configuration of the rest of the universe is such that it gives rise to this conditional wave function psi. But we do not have to condition on the exact configuration of the rest of the universe, which would be ridiculous. We just condition on the fact that the wave function of the subsystem is what it is. And then we get here again the chi-square measure. And then, analogous to the case of the Maxwell-Boltzmann distribution of statistical mechanics, we can then derive from that law of large number statements. So we look at an ensemble of subsystems prepared with identical wave function psi, and we look at the distribution of particle configurations in this ensemble. So we have here again a characteristic function. So this expression here for a given configuration of the universe just counts the number of subsystems whose configurations is in the set A. And this is just to very good approximation given by the chi-square measure integrated over the set A. Oh, and here is a typo. This must be larger than. So the set of configurations of the universe for which this deviation is larger than epsilon, of course, goes to 0 as n goes to infinity. This is just a law of large number statement. And now we have to think about what this mathematical result means. So this chi-square, this measure here is defined as the chi-square measure given by the universal wave function. So this result means that Born's rule holds for ensembles of subsystems in typical Bohemian universes. That means in quantum equilibrium. Or in other words, Born's rule holds as a statistical regularity for ensembles of subsystems for almost all possible initial conditions of a Bohemian universe. And the role of this chi-square measure given by the universal wave function is precisely to define typicality. It's precisely to define what we mean by typical Bohemian universes, or in other words, what we mean when we say that Born's rule holds for almost all possible initial conditions of the universe. And yes, that's the right question here, and the answer is that why do we take this chi-square measure? Because this measure is distinguished as the unique stationary, that means equivariant measure, for the Bohemian dynamics. So this is proven that in a very large class, very natural class of possible measures, this chi-square measure is the unique measure that is compatible with the Bohemian dynamics. And of course, you want a stationary or equivariant typicality measure because the universes, if you make a typicality statement and say that a particular property is typical, you do not want the statement to depend on time. The typicality statement should be time independent. So this typicality measure is distinguished by the fact that it's the unique stationary measure for the Bohemian dynamics. Just as so in some sense the situation is even better than in classical mechanics, because in classical mechanics you have many stationary measures for the Hamiltonian dynamics, and just the Lebesgue measure is just the simplest one, the most natural one. In Bohemian mechanics, the stationary measure, which is the typicality measure, is even unique in a rather strong sense. And this is why we use it as a typicality measure. Yes. Yeah. Yes. No, it doesn't, but here we have a different setting, so we do not have a fundamental collapse, we have just an effective collapse. No, you just want so we do not talk here, so first we do not talk here about probability, because this is a measure on the configuration space of the universe. We do not want to talk about probabilities or frequencies when we talk about the universe. We just want to say what is true for typical universes. So what is true for almost all possible initial conditions of the universe. And the role of this measure is just to define what we mean by almost all possible initial conditions. So the distribution of particles that we find in the world is completely determined in this theory by the initial condition of the universe. Nonetheless, there's a typicality law for almost all possible initial conditions that could be the initial conditions for our universe. The distribution in subsystem is such that we find Born's rule. And the role of this chi-square measure is just to be a typicality measure and to define what we mean by almost all possible initial conditions. And we need some measure as soon as we have a continuous state space. We cannot just count the states, so we need some sort of measure. And then the question is, what is the natural measure? And the natural measure is the stationary measure, the one that doesn't change within time under the dynamics. And as I said, in some sense, the situation is better. So this chi-square here measure, the status of this measure is the same as the status of the Lebesgue measure in classical statistical mechanics. And in some sense, the situation is better than in classical mechanics, because we have here uniqueness of the equivariant measure. In one pedagogical sense, the situation is worse, because it so happens that the functional form of the statistical law for the subsystem of Born's rule, right, is psi square for the conditional wave function, and the typicality measure is psi square for the universal wave function. So it looks to many people as if you put psi square in, you get psi square out. But this is to some degree an unfortunate coincidence, right? So in classical statistical mechanics, we put in here a homogeneous measure, homogeneous typicality measure, and we got out this Gaussian measure, the Maxwell-Boltzmann distribution, okay? So there you did not have this coincidence that you have the same functional form for the probability measure and the typicality measure. In Bohemian mechanics, it's a bit of an unfortunate, from a pedagogical point of view, coincidence, but you have to understand or try to appreciate that these measures have a very different status. So, sorry. This little phi square measure for the subsystems that describes actual statistical distribution frequencies of subsystems that exist in the universe. Okay, this measure here is just a typicality measure which defines what we mean by almost all initial conditions. This does not define an actual ensemble or an actual distribution of anything because, as I've repeatedly said, our universe exists only once. There's no distribution of initial conditions of universe. So this is a typicality measure. This is an actual distribution that we find for subsystems in the universe, and we explain Born's law by realizing that Born's law is the distribution for particle configurations in subsystems that we find for almost all possible initial conditions of a Bohemian universe. Okay, this is quite subtle, so I needed a long time to appreciate this, and it's normal if you do not feel completely at ease with this, but well, it is really very much along the spirit of Boltzmann's statistical mechanics in classical statistical mechanics, and this, for me, it is a very, if you digest it, it is a very strong argument for Born's rule in Bohemian quantum mechanics. If you want a typicality measure, it should be stationary. And if you want a stationary measure, it has to be the psi-square measure for the universal wave function. Sorry? Well, typicality is a way of reasoning, so to speak. You observe a regularity in the world, and you want to explain why this regularity holds. And you explain this regularity. So what you couldn't do is, if you knew the exact initial condition of the universe, and you could solve the exact equations of motion for the universe, you could thereby check if this regularity obtains in our very universe. But of course, we cannot do this. And even if we could do this, you might still wonder, why is the initial condition of the universe exactly as it is? Right? Why is the initial condition of the universe such that it gives rise to a psi-square distribution for subsystems, as we observe that? Right? Even if you knew the exact initial conditions of the universe, you might still wonder why this is the case. But then you make a typicality reasoning, which is a stronger reasoning, namely saying that it's not only the case that for our actual universe, the initial condition was such that it gives rise to Born's law in subsystems, but in fact, almost all possible initial conditions would have given rise to a universe in which we observe Born's law as statistical regularity. This is a very strong statement that is very explanatory, because there's now no sensible mystery anymore. Why was the initial condition such that, of the universe such that it gives rise to Born's law? Right? Because almost all possible initial conditions of the universe will give rise to Born's law. This is the argument. And now the question is, what do you mean by almost all possible initial conditions? And since we have a continuous space and we cannot just count, we need some sort of measure that tells us what do we mean by almost all. And a natural requirement for this measure is stationarity property. And that, gives you uniquely the psi-square measure in the case of the Bohemian dynamics. so you could, so the thing is, so in classical mechanics, we have some sort of mystery, which is that according to classical mechanics, our universe is not in equilibrium, right? That's why we have a thermodynamic error of time. This is why we have increase of entropy. So this means that according to this classical statistical analysis, our universe did not start in a typical initial condition, but in a special initial condition, in a low entropy initial condition. And this is actually a problem. This is actually, I would say, one of the deepest issues that we face in physics. Why does it seem, at least, that our universe started in a very low entropy state? And then you have results. But if you start in a low entropy state, for instance, you start with the gas in a box in which all the particles are in one side of the box, so not homogeneously distributed. You have convergence to equilibrium, just because almost all possible initial conditions will evolve into the equilibrium state. So in Bohemian mechanics, we do not have this issue because it appears that with respect to the Bohemian dynamics at least, our universe is in equilibrium already. So we do not have to talk about convergence to equilibrium because Born's law that we observe is already a typical feature. And with respect to this feature, to the statistics, our universe is already in equilibrium. That is why we say quantum equilibrium. That said, you can also show, or there are also results, that if our universe would not have been in equilibrium, right, you would have convergence to equilibrium. So if we live in a Bohemian universe that started out of equilibrium in a special state, we would have convergence to equilibrium in a thermodynamic state. This is in particular Valentini who makes this kind of arguments. But in some sense, there's no need there's no need to assume that our universe started in non-equilibrium in a very special state, right? Because our universe is already in quantum equilibrium in a typical state. So there's no need to assume from a Bohmian analysis that our universe did not start in a typical state. It would be a mystery somehow if it did not start in a typical state, as it is a mystery according to the classical statistical analysis. I'm not sure if this answers your question. Okay. So this is not running. How much time do we have? Yeah, there's another question. No, this is not what I said, I guess. I didn't speak about initial probability, I didn't speak about uncertainty, so for our universe is a fixed value. Our universe has one configuration that evolves deterministically according to a deterministic law. So there's no probability distribution for the configuration of our universe. Our universe has one state and one state only, right? Our universe is what it is. And the configuration of the universe as a whole determines, of course, distribution of particles in subsystems. But now we find a regularity in this distribution of positions in subsystems. And this regularity is expressed by Born's law. And now you can wonder, you have to ask the question, why do we find this regularity in the world? And the answer is because this is the regularity that you would find for almost all possible configurations of the universe. almost all possible initial configurations of the universe are such that Born's law holds in subsystems. So Born's law is a feature of typical Bohemian universes. And this explains why we should by all reasonable means expect to find it in our actual universe. Okay? Yes? Yes? Sorry? Yes? 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 So again, if you have an ensemble, if you have an ensemble of subsystems that is not distributed according to psi square, then in principle, you would have convergence to equilibrium in the sense that under the Bohmian dynamics, it would evolve into a distribution that is psi square. But we do not find the situation in the first place because it is atypical. It would be atypical to find an ensemble of Bohmian subsystems, right, identically, independently prepared with the same wave function or with the same conditional wave function, which is not distributed according to psi square. So that you could even find such an ensemble, our universe would have had to start in a very special initial condition. But our universe did not start in a very special initial condition. It started in a typical initial condition. And for typical initial conditions, there are not even ensembles of subsystems where you do not have this psi square distribution. This is like having a box of gas in which the particle velocities are not distributed according to the Maxwell-Boltzmann law. It is possible. It is possible even we could have a box of gas in which the particles all move with the same velocity, right? In which the particles all move with the same velocity. This is possible, right? But it's an extremely special initial condition, obviously. An extremely special initial condition that gives rise to particles in a box moving all with the same velocity. And this is, of course, a pathological case. You could conceive of other cases where the velocity distribution differs significantly from the Maxwell-Boltzmann one. But those are all extremely special configurations, corresponding to extremely special initial conditions. But for almost all possible initial conditions, for almost all possible microstates that the gas could be in, you will find the Maxwell-Boltzmann distribution. Similarly, or analogously, for almost all possible initial conditions of the Bohmian universe, you will find the Born's law. You will find Born's law for subsystems. If our universe were such that, so our universe would have to be very special, very fine-tuned, so to speak, to allow you even to find ensembles of subsystems in which Born's rule does not hold. This is the point of the typicality argument. Yeah. Yeah, that would be great. So let me mention one important result, which is absolute uncertainty. And this is a feature that follows from quantum equilibrium analysis. So it is a theorem that in quantum equilibrium, and again, our universe is in quantum equilibrium, you cannot have more precise information about the configuration of the system with wave function psi than what is given by a psi square distribution. Okay? This is why, for instance, in the example of the spin measurement, okay, that we considered yesterday, you cannot cheat your way out of the quantum statistics, basically, by measuring the initial position of the Bohmian particle and then arranging your Stern-Gerlach magnet in such a way that you always get spin up, let's say. cannot do this because by the laws of nature, it follows that you cannot know the initial configuration of the Bohemian system better than what is given by the quantum probabilities. And this is a very simple but elegant argument. The reason is that your information about the subsystem that you have, it must be stored somewhere. It must be stored somewhere in the configuration of the rest of the universe. This configuration of the rest of the universe includes the configuration of your brain, if you will, or the configuration of your computer, or the configuration of your measurement apparatus, or the configuration of your lab notes, which you noted the results of your measurements. So all the information that you could have about the distribution of the subsystem of interest is already encoded in this configuration of the environment Y. Right? But this is already taken into account in this conditional probability formula when we have here conditioned on the actual configuration Y. Okay? So condition here the probability, or rather the typicality measure, on all the information you have about the subsystem. Right? All the information that you could have about the subsystem is already contained in this Y, and yet the conditional measure is still the chi-square measure. This is a very simple but important argument that from the statistical analysis, it follows that you cannot have more information about the actual configuration of the subsystem than what is provided to you by Born's rule. And this comes out from the statistical analysis of the system. So now let me talk briefly about operators. So as you may have noticed in the formulation of our theories, and now I'm not talking exclusively about Bohemian mechanics with suitable modification, what follows holds also for Collat's theories, or in fact for, I think, every precise formulation of quantum mechanics. We did not talk about operators, we did not talk about observables, we just talked about a precise evolution law for the fundamental ontology. But now, what we usually call operators or observables, they just arise from a statistical analysis of the field. And you should note that this notion of observables, right? So in physics, somehow we have mixed together the notion of observables, meaning both observable quantities that we observe in nature and self-adjoint operators for some reason. This is basically what we call observables, but it's a weird concept. So why should any laboratory procedure be associated with a linear operator on Hilbert space? Right? This is just a postulate of standard quantum mechanics, but if you think about it, it's a rather weird postulate. Why should some laboratory procedure that corresponds to a measurement be associated with some operator? How does the experimentalist even know how to measure a particular operator? Okay, go to an experimentalist, write down some self-adjoint operator and tell him, measure that. It doesn't make any sense. Okay, usually we basically know what it means to measure an observable, measure an operator, because we think about them in classical terms. And we think about the operator as a quantization often of the classical observable. But this has it upside down. Okay? Quantum mechanics is the fundamental theory, not classical mechanics. So then you could ask, do all self-adjoint operators correspond to measurable quantities? And if not, which one do? And do all measurable quantities correspond to self-adjoint operators? And if not, which one do? So these are all questions that a precise analysis, I think, should answer. And now we will look at a scheme which is a bit idealized, a bit simplified scheme of ideal measurements in quantum mechanics. And I want to propose to you a definition, which is maybe somewhat more of an assumption, namely a measurement apparatus. What we mean by a measurement apparatus is a macroscopic system, a quantum system, of course, because we talk about quantum mechanics, that interacts with another system and evolves, depending on the state of the measured system, into one of several macroscopically distinct states, which we always simplified. We speak about pointer positions. In the end of the measurement, the pointer points to the left or the pointer points to the right, corresponding to one of the possible measurement results, alpha of k. So in quantum mechanics, of course, the macroscopically distinct states, so corresponding to the measurement results, alpha k, correspond to well-localized wave function, phi k, with mutually disjoint supports. This is a bit of an idealization, but it's a very natural stipulation how we can think of a measurement apparatus. And now an ideal measurement, this is basically all for Neumann, works like this. A system couples to the apparatus under the Schrödinger evolution, so this phi 0 being the ready state of the measurement apparatus evolves into one of the pointer states, here denoted by phi k, indicating one of the possible measurement results. So the pointer pointing to alpha 1, to alpha 2, and so on. The system may be, of course, in a superposition, so we can write we can have a sub-wave function for the subsystem which has this form, and then the Schrödinger evolution of system and apparatus will also involve into a superposition of the system wave function and the apparatus wave function. This is, of course, the root of the measurement problem that we discussed yesterday. And the fact that the apparatus wave function correspond to different pointer positions, okay, means that they correspond to well-disjoint regions in configuration space. So these different terms of the superpositions, they do not overlap in configuration space. In other words, we have decoherence, okay, because the wave function of a pointer pointing to the left and the wave function of a pointer pointing to the right, they are localized in disjoint regions of phase space, of configuration space, sorry. And again, this does not solve the measurement problem because still both parts of the wave functions are there, but in Bohemian mechanics, the actual configuration of the subsystem is either here or there. And in a collapse model, after the measurement with extremely high probability, the wave function will collapse, leaving us with just this part of the wave function or that part of the wave function. So those are solutions of the measurement problem. But now we can, for instance, in Bohemian mechanics, just simply compute the probability of a measurement outcome alpha j. This is just the probability that our actual configuration y is here the actual configuration of the measurement apparatus, so that the actual configuration of the measurement apparatus is in the support of phi j, meaning just that the pointer position is such that it indicates the measurement result phi j, and we just take here the Bond's rule, the chi-square distribution, and we square this expression, and then the off-diagonal terms, or the mixed terms, they vanish because phi k and phi j have disjoint support, leaving us just here with this term, and which just gives the probability Cj squared to find the measurement result alpha j, okay, corresponding here to this phi j part of the superposition. This is just Bond's law. Applied to the situation where we want to know what is the probability that the pointer actually points to a particular result, in this case alpha j, and the probability is Cj squared. And now comes a simple but important observation for the conservation of measure. Okay, we have the probability, the total probability is conserved. So we have here the total probability of the initial state. This is just the superimposed the wave function of the microscopic system coupled to the ready state of the measurement apparatus, and we just compute that, and under the time evolution, it evolves into this superposition with the different pointer states, but again by orthogonality, by decoherence, the cross terms vanish, and we have just here the sum over, basically the sum over ck squared. And now by multiplying this thing here, we see that here the cross term vanishes, right? Here the cross term vanish by macroscopic decoherence because the different pointer positions, different pointer states have macroscopically disjoint support, leaving us only with the sum over the ck squared. But if they vanish here, then by conservation of probability, they have to vanish there also. So this implies that here the sum of this cross terms for the microscopic wave function, right? These here are all just multiplied with the ready state of the measurement apparatus. But this is 0 also. And if this is 0 also, and this holds for arbitrary coefficients, it is relatively easy to show, this is just linear algebra, that every single term must vanish. And that every single term must vanish now just means that there's different parts here of the microscopic wave function that lead to different measurement results, so that lead to macroscopically discernible pointer positions. They must be orthogonal to each other. This just comes out of this measurement analysis together with the conservation of measure. Note that we did not assume in this, I did not assume in this superposition that this is an orthonormal basis. Okay, this is not an assumption here that the states are orthogonal to each other. But it comes out that if these states lead to macroscopically disjoint measurement outcomes, they must be orthogonal to each other. This comes out of an analysis. So the proposition, the theorem that we derived is that if the system wave functions phi1, phi2, and so on lead to macroscopically distinguishable measurement results, they must form an orthonormal system. And since they form an orthonormal system, we can consider for each one just the orthogonal projectors. So this is just an operator, an orthogonal projection on the state phi k, leading to the measurement result alpha k. And then if we want to know the probability for the measurement result alpha k, we just sandwich our state here. So we just sandwich this orthogonal projection into our state phi, and we compute here the probability for the measurement result alpha k. And this is just as before, ck squared. So before we computed that explicitly from Born's rule just for the position of the pointers. And here we have now a more compact form given by this orthogonal projector. This is the probability for the measurement result alpha k. And then what is the expectation value of this measurement that we have just performed or analyzed? Well, we just have to, the expectation value is of course nothing else than the sum over alpha k times the probability of alpha k, which is that. And we get this if we sandwich between our state here a sum of alpha k, right? This is just the value of the measurement result times the orthogonal projection on this state that leads to the measurement result, alpha k. But this here that we have written down here is nothing else than the spectral decomposition, the mathematician would say, of a self-adjoint operator that we can call here A. Okay, so we can introduce the self-adjoint operator A, and in this self-adjoint operator A, we have in a very compact form everything we need to know about the statistical description of this measurement. Okay, its spectral decomposition of the self-adjoint operator gives you the probabilities for all the outcomes, and the operator just sandwiched between this state phi here gives us the expectation value. Okay, but now if you start from this operator and think somehow that this operator is fundamental, you have it upside down, so to speak. Okay, this operator is not fundamental. This operator is just a good bookkeeper, an efficient bookkeeper of our measurement statistics that just came out of an analysis of the theory. Okay, for instance, we have here the example of a spin measurement, again, that we saw yesterday. We have here a superposition of spin up and spin down, just with weight alpha and beta, and the Stern-Gerlach magnet does nothing else than to split this wave function into two wave packets. So the wave packet corresponding to the spin up spinor goes to the left, the one corresponding to the spin down spinor goes to the right. And now, if we want to know if we measure spin up or spin down, we just have to compute the probability that our particle is in the support of this wave packet. This gives us the probability for measuring spin up, or the probability of that our particle is in the support of this wave packet. Okay, here we do not have to even consider, strictly speaking, the wave function of the detector of the measurement apparatus, because already the wave function of the subsystem, they have disjoint support in space, so it suffices to ask with what probability is our particle here and with what probability is our particle there. In the Bohemian context, in the context of the collapse theory, the question would be slightly different. With what probability does the collapse strike somewhere here in the concept, in the support of this wave function, of this wave packet, and with what probability does the collapse strike, does the collapse hit somewhere here in the support of this wave packet? So what we say here applies mutandis, mutatis to collapse theories, if you will. And this is now just a simple computation, right? So the probability that our particle is somewhere here is just the psi square measure integrated. So it's just the psi square weight of this wave packet, and the probability for spin down is just the psi square weight of that wave packet. And you can just write it again with projectors if you want. So the probability for spin up, you just get by projecting on the spin up component and integrating, right, giving you the psi square probability, where we have introduced this projector onto the spin up component, and the probability for the particle being in the spin down wave packet is just here the integral over the support of this wave packet, which is the same that we get by projecting on the spin down component. And if you want to know the expectation value, okay, it's just h bar half times the probability of having spin up minus h bar half plus the probability of having spin down. And you can write this again in this compact form with these two projectors, right? This projector minus that projector, and you get the famous Pauli matrices, the famous spin observables. Okay, again, the spin observables are not something fundamental, something that we have to postulate as to include into the postulates of our theory. They just come out as bookkeepers naturally from a statistical analysis. And here is a point that maybe I should have stressed yesterday. So in Bohemian mechanics, a spin is not a predetermined property of the particle. A spin is a property of the wave function. So this spin wave packet, corresponds to the spin up spinor, and this wave packet corresponds to the spin down spinor, and they separate in this inhomogeneous magnetic field, and the particle follows either one or the other. And that determines whether we say that the particle has spin up or if we say that the particle has spin down. But this does not mean that the spin is a predetermined property of the particle that we should be, so to speak, realists about, right? And this explains basically all these no hidden variables theorems. Okay, in general, it is true that the measurement results of a quantum experiments, they do not reveal predetermined properties of the measured system. In some sense, they create these properties of the measured system. In the spin measurement, we in some sense create the property of having either spin up or spin down, by separating the wave packet into the spin components and forcing the particle to follow either one or the other. But to see that the spin is not a predetermined property of the particle, we can look at this funny setup. So we have here first the Stern-Gerlach magnet splitting the wave packets into the spin up part and the spin down part. And then sometime afterwards, okay, we put the Stern-Gerlach magnet oriented in the opposite direction. So here the spin up part then goes down and the spin down part goes up. And now you can ask, what is the trajectory of the Bohmian particle? And remember, we have here a fairly symmetric setup, and we have the no crossing property of the Bohmian trajectories that we discussed yesterday. Okay, so a particle that hits the screen here in the upper half, since trajectories cannot cross, a Bohmian particle that hits the screen here in the upper half has moved like this here, and here he cannot cross the symmetry line, so he goes into the support of the wave function coming from down and moves up again. Okay, so one and the same particle, this means, is first guided by a wave function with spin up, and here it is guided with a wave function corresponding to spin down. Okay, so the Bohmian particle switches the support and is first supported, it is first guided by a wave function with spin up, and it is then guided by a wave function with spin down. And this should show very clearly that it would be wrong to think of the spin as some predetermined property that is intrinsic to the particle. It is not. Yes? Sorry, the status of? Here, it is neither. That is the whole point. Spin is not a predetermined property of the particle. Bohemian mechanics explains why it is not. It is just a measurement apparatus, in this case the Stern-Gerlach magnet, that forces, that makes the wave function split according to the spinor components, and it forces the Bohmian particle to follow either one or the other wave packet. But spin is not an additional degree of freedom of the particle. It is, just as in quantum mechanics, though, in some sense, the degree of freedom of the wave function, and that the wave function, if we have fermions, is a spinor valued wave function. But this is the whole point. Spin is not an additional internal degree of freedom of the particle, and it does not correspond, a spin measurement does not reveal a predetermined spin property of the particle. Yes, and according to quantum mechanics also, but you kind of don't know what this means in quantum mechanics. But this is what quantum mechanics, this is the mantra of quantum mechanics, and this is what all these no hidden variables theorems show, right? That these observables do not correspond to predetermined quantities that are just revealed in experiment. You cannot think of them this way. But in standard, so this is something that standard quantum mechanics teaches us, and standard quantum mechanics is right about that. But if you have a more precise formulation of the theory, such as Bohmian mechanics or a collapse models, you understand what the statement means. You see here why indeed spin is not a predetermined property of the particle. Just our spin measurement, the Stern-Gerlach magnet, forces the wave function to split according to the spin components, and thus the particle will follow either one or the other wave packet, corresponding to it having either spin up or spin down. Or if you want to express that in terms of the collapse theories, the Stern-Gerlach magnet that we put there, again, forces the wave function to split according to the spinor components. Spin up component moves up, spin down components moves down, and then when the collapse event strikes, it forces the wave function to localize either on the spin-up component or on the spin-down component. But here too, spin is not a predetermined property of the particle. And now there's a more general measurement scheme where you can make such an analysis. And okay, good. I guess I don't have that. Yeah, let's mention it just briefly. So the general scheme is this. You have a system wave function that couples to an apparatus wave function. They evolve according to the Schrödinger evolution into some state. It might be a product state or not. And then for this evolution, you have Born's rule that gives you the typical distribution of configurations in this combined system plus apparatus. And then what we care about are the values of certain random variables. Here f is what a mathematician would call a random variable, but it's really nothing else than a coarse graining function. It means we can ask, for instance, in this configuration, is the pointer pointing to the left or is the pointer pointing to the right, for instance. This would be mathematically represented by this coarse graining function, okay? Mapping all possible configurations of system plus apparatus into the state, let's say, pointer left or pointer right. This is coarse graining, okay, because many possible configurations of the apparatus correspond to the pointer pointing to the left or to the pointer pointing to the right, okay? And we just care about the probabilities. What is the probability that in the end we end up in a configuration such that the pointer points to the left, let's say, or such that the pointer points to the right. And then it's just a simple mathematical observation that this mapping here, the sequence here, is sesquilinear in phi. So this is a quadratic form which is sesquilinear in phi. And so we have here the probability for, well, some range of values dA. And this mapping is sesquilinear in phi. And because it's sesquilinear in phi, it just follows mathematically that there exists a positive operator such that you can write this probability in this form. So you have here the scalar product phi times this operator, depending on this set of measurement values, and again phi. And for an arbitrary measurable set A, so A is just part of the possible outcomes of the experiments, well, you basically just sum up or integrate here over the set A, and you have here an expression of the following time. And those here are then operators acting, positive operators acting on this wave function. And it's relatively straightforward to check the properties. For instance, here, if you take the operator associated to all possible outcomes, to the set of all possible outcomes, it's just, well, integrated over any wave function phi. It is just gives you just one. So you have here the identity operator, and if you have disjoint sets of outcomes A and B, then the associated operator is just the sum of operators associated to A and operators associated to B. And this is what one would call mathematically a positive operator valued measure. So this is something that is now very important in measurement theory and quantum mechanics, also to some degree in mathematical physics. It's a bit fast here, but you can see how this arises very naturally from the analysis of this theory. So for example, the problem associated to a position measurement is just given by the characteristic functions of a set. So you just integrate, of course, the chi-square measure, over the set A. And in this case, the positive operator valued measure is really a projector valued measure corresponding to a self-adjoint operator. But the point here, and I'm sorry, just for time constraints, I'm going a bit fast, but the point here is that not all positive operator valued measures are projector valued measures, so not all measurement statistics are described by self-adjoint operators. Okay? In the general case, measurement statistics are described by these POVs, by these positive operator valued measures. And in the case that the positive operators are not projectors, so they do not satisfy this projector property here, that the square of each operator equals the operator itself, then they do not correspond to the spectral decomposition of a self-adjoint operator. So although this is still a statement that you will find in many textbooks, that all measurement statistics in quantum mechanics correspond or are given by observables in the sense of self-adjoint operators, it is now widely understood that this is in fact not true. Some experiments, or in general experiments, are described by these POVs, by positive operator value measures, and not necessarily by self-adjoint operators. And one example here is an imprecise position measurement. So you just get the chi-square distribution if you assume that you can measure the position or the configuration of the system without error. So let's assume that we have a certain measurement error. This is also random. So the actual measured position then is formally the sum of x plus y, where here x corresponds to the actual position, so distributed according to chi-square, and y is a random measurement error that has a probability distribution R. And then the distribution for the measured position, which I called here x tilde, is then given by the convolution of R with chi-square. This is just, it's not completely obvious, but it's just standard probability theory. If x has distribution chi-square and y has distribution R, then the distribution of their sum is given here by the convolution. So this means that the probability for our measured value lying in some range of values A, okay, is just the integral of this distribution here over the set A. So that's here. I think just here we have just inserted this expression with the convolution, and instead of writing here this A under the integral sign, we introduce here the characteristic function, which is 1 on the set A and 0 everywhere else. So this just equals this integral. So you see here, this is just the integral over psi squared multiplied by this expression. And this expression is then the positive operator valued measure corresponding to this set A. This is then the corresponding positive operator valued measure for every set A. We have an operator. This is an operator that just acts by multiplication. Just multiply this term here with psi, right? This is the POVM corresponding to this imprecise position measurement, and this operator in general does not satisfy the projected property. So the square of this operator is not the same as the operator itself. So this POVM is not a PBM and does not correspond to a self-adjoint operator, to what one would call a classical observable in quantum mechanics, but it gives you the right statistics for this imprecise position measurement. So this is a generalization of the measurement schemes, and again, these POVMs come out naturally from an analysis of the theory. So here, to end with something more conceptual, an important quote from John Bell. So he, I think we mentioned it yesterday, introduced this word beables as a play on words on the term observables, right? So he said, the concept of observable lends itself to very precise mathematics when identified with self-adjoint operator. But physically, it is a rather woolly concept. It is not easy to identify precisely which physical processes are to be given the status of observations and which are to be relegated to the limbo between one observation and another. So it could be hoped that some increase in precision might be possible by concentrating on the beables, which can be described in quote-unquote classical terms because they are there. The beables must include the settings of switches and knobs and experimental equipment, the currents and coils, in the readings of instruments. Observables must be made somehow out of beables. The theory of local beables should contain and give precise physical meanings to the algebra of local observables. And again, Bell's famous term of local observables is just what I called ontology or primitive ontology. Those formulations of quantum mechanics that I consider to be precise formulations, they do not put observables at the beginning. They put a precise ontology at the beginning, at the top. They make predictions about what is actually there, about stuff in physical space, including in particular the configuration of your measurement apparatus, pointer positions, computer readings, display readings, computer prints, etc. And thus, they account for all observable phenomena. And the observables can just come out from a statistical analysis of this theory. So here are some takeaways, just a bit pointed statements. So the standard quantum formalism just follows from a statistical analysis of Bohemian mechanics. And I would add also the GRW theory or precise collapse model. Gives you also this operator formulas in this way. So Born's rule is a regularity of typical Bohemian universes. This is how we explained the quantum formalism. And this is a bit of a provocative statement. Now, if the quantum formalism is correct, if the statistics are correct, Bohemian mechanics is most likely the correct microscopic theory that gives rise to this formalism, that grounds this formalism. But again, always keeping in mind that if the collapse models are correct, then the quantum formalism will fail on some scales. This is also a possibility that we discussed yesterday. The quantum formalism might be wrong on large enough scales, and then this would be a good argument for the collapse. So operators, or rather POVMs, arise as bookkeepers of measurement statistics. And here I think a very important point to keep in mind. So the mathematical attractiveness of the operator formalism can easily suggest that operators must play an important and fundamental role in quantum theory. Operators are mathematically very nice and they are physically very powerful, and you can study them for years. They give rise to pretty nice mathematics. So this might suggest that they must play an important role, an important and fundamental role in quantum theory, but they don't. If you have a precise formulation of quantum theory such as GRW, such as Bohemian mechanics, and also I might add maybe the many-worlds theory, you will see that operators are efficient tools, nice bookkeeping tools, but they are neither fundamental nor important. So observables, as Bell taught us, must come out of beables. It's not a good idea to formulate a theory in which the notion of measurement or observation is fundamental, because measurement and observation is itself a complicated physical process that must be understood in terms of theory. So we think that a better idea is to have a theory that puts the beables at the beginning, that puts an ontology at the beginning, that talks about what the theory postulates to exist out there in the world. Then you analyze the theory, and the theory tells you what the observables are, and what the measurement statistics are, and so on and so forth. So if a theory describes correctly the distribution of matter in time and space, everything else follows. Right? If a theory predicts correctly for instance, the position of all the particles, in particular those that compose your measurement apparatus and your computer display, and so on and so forth, then it makes the correct predictions about everything that you will measure in the laboratory. And this is also a rather surprising insight. So in the end, at least according to Bohemian mechanics and to some degree also according to the collapse theories, every measurement is a position measure. Okay? If you know in the end, what your measurement apparatus will show you, and if you can account for that and give the right statistics for that, then you have the right predictions for everything that Okay, I hope I'm not too much over time, and I'm still here for questions, and well, thank you very much.